So in this problem, let me draw the diagram. We have an incline. Alright, so on our incline we have an angle theta, and we have a pulley, and of course it's going to be massless and frictionless, and we have a mass hanging off of it, and let's call this C, and it's of mass capital M, and then over here we have two masses connected by a rope, and this is A, and it's mass little m connected to B, mass also little m, and it's connected over the pulley to mass C. So the question is, in the diagram below, right here, block A is attached to block B by a light cord, and block B is attached to block C by a light cord, ran over a massless frictionless pulley. The angle of the incline is given by theta, and the mass of the blocks A and B is little m, and the mass of block C is capital M, where capital M is greater than 2 little m. So this basically lets us know that this will be moving downward. So first thing we want to do is set up our coordinate axis. So for this, our coordinate axis is going to be the upward direction is positive for our forces and acceleration, and here the upward direction is positive. And intuitively, we know this mass will be moving downwards, so the acceleration of block C will be negative because it's moving down, because we said positive is up. And then the opposite is true here. This is moving to the right, that's positive, so the acceleration here will be positive. So the first thing we want to do is, the question is, find the acceleration of block B, assuming the surface is frictionless. So the first thing we want to do is write our force diagrams. So I'm going to draw 3 of them and then erase the diagram so I have room to calculate it. So first, on the incline, I'm just going to do the non-component forces. Downward we have gravity, mg. Downward, sorry, nothing downward. We have normal force upward, and we have tension 1. We have 2 tensions, because we have tension between A and B, and a tension between B and C over the pulley. So I'm just going to put that there for now. So we have 2 tensions. So now I'm going to break up these components, break these up into 2 components. So for A, instead of having mg downward, what we have is mg cosine, because of the way the trigonometry works out. And a little way to remember this is that it's either going to be cosine or sine, but the sine is always slipping, right? It starts with an S, so it will always be going down. The slope is sine. So to the left is mg sine of theta, and upward we have normal force, and to the right we have our first tension. So that's A. Now for B, I'm going to draw it over here. It's the same thing, because it's on the same incline, it's in the same mass. The only difference is we have 2 tensions on block B. So let me draw this out. Upward normal force, to the right is tension 2, downward is little mg cosine of theta, and to the left is mg sine of theta, and this is the important part, T1. So that's A and B. And now we have C, I'm going to draw it down here. The only forces acting on C are tension 2 and capital Mg. So before I erase this and go into Newton's second law, it's important to recognize that we have tensions that kind of repeat themselves. We have T1 here, but it's also here. T2 here, it's also here. So it's good to see that what we're going to have is end up having a system of equations. So we'll get to that in a second. Now let me erase the board. Okay, so we want to write Newton's second law for each block. So basically what we're going to do is for block A, we're going to have the sum of the forces equals MA for block A. For block B, it'll do the same thing. And then for C, sum of the forces equals capital MA. Now, what we need to see is that the acceleration of A and B will be the same, because they're on the same incline, they're both traveling upwards, so their acceleration is positive. However, if you remember on our diagram C, the downward direction is negative, so it's actually going to be negative acceleration. And all the accelerations are the same because the pulley is massless and frictionless. So these are positive accelerations, and this is a negative acceleration. So now we can begin our systems of equation. So for block A, we have, going to the right, we have tension 1 minus mg sine of theta equals little ma. Then over here for B, we have T2. Now this is important. Always make sure you know what you're doing with your math, because To the left, you had two quantities, t1 and you had the mg sine theta. So we're going to have two things in parentheses. Plus tension 1. And that's going to be equal to little ma. So I'm going to solve these out first, and then we're going to go back to C. So the first thing is that T1 is equal to mg sine of theta plus little ma. So that's one relationship, so it's one variable found because we have it in terms of our given variables. Now we need to find T2. So I'm going to bring this down over here, so we're going to do C right here. So the forces on C are just T2 minus capital Ma equals capital Ma. So this is a mg. So T2 is really just equal to capital Mg minus capital Ma. So now we have our T1 and our T2. So all that's left is to plug it into our equation for B, because remember the question says the acceleration of block B, and then using that we can solve for A. So this is going to be quite a bit of algebra, so it's always good to keep track of your variables. So T2 is going to be a positive Mg and a negative Ma, minus, all this stuff is in parentheses, so don't forget that, little mg sine theta plus Ma plus another mg sine theta. That's going to be all equal to Ma. Okay, so this is quite a bit to work with, and I'm going to get rid of some terms to make it easier to see. So here we have two mg sine thetas. So I'm just going to start there. So mg minus Ma minus 2 mg sine theta plus little ma equals Ma. So now it's just going to be more solving. So I'm going to get all my a's on one side. So I'm going to have mg minus, I'm going to distribute the negative, so minus 2 mg sine theta minus Ma. This is going to be capital M plus little m times A. Right? So then, now we have to do is get this A over here, and then we're done. So we're going to have capital M g minus 2 little mg sine theta equals capital M plus, now 2m times A. And then we're just going to divide this off, and then we have our acceleration. So A is ultimately equal to, I'm going to pull out the g's too, so we can have a bit more simplified of an answer. So g times capital M minus 2 little m sine of theta, parentheses, all divided by capital M plus 2m. So this is our acceleration. And now a quick logic check would be that, well, is this acceleration positive? The answer is yes, because we're traveling in the upward direction. But if we think about it, our masses will always be positive. You can have negative mass. Gravity is going to be negative, but our larger mass minus the smaller mass times the sine of the angle will end up being a negative number here, so we'll end up with a positive over a positive. So that's a quick way to limit check your answer to make sure you got it right. Now the surface has friction of coefficient u of k, and the core between A and B is instantaneously cut by a laser. So find the acceleration of now block C, which is still attached to B, and of block A, which is sliding down the incline with only friction acting on it. So let me draw that again. So this time, we have our incline of angle theta, and a pulley with block C of mass capital M, only attached to block B of little m. And A is all by itself, sliding down the incline, independent of these two. So this is basically just two separate problems. So let's start with A. So the free body diagram on A is kind of like it was before. Down we have little mg. To the left, which is down the incline, and before we do anything, let's actually set our coordinate axis again. This is the positive direction, and this too is the positive direction. So for this, I'm going to set a separate coordinate axis just for A, because the movement of these is independent from this. So for this, just for A, this is going to be positive downward, because it'll save us some time. So downward, I'm going to call this, downward we have mg sine of theta. Remember, it's slipping down the incline. Backwards, we have the force of friction, which is a resistive force. And lastly, we have the normal force. So from there, we go to our free body diagram. So sum of the forces equals little m A. So the first thing we're going to do is we're going to write our horizontal forces, because that's what we're concerned about. Is it moving downward at what acceleration? So we're going to have, remember this is positive, is this direction. So it's going to be mg sine of theta minus force of friction equals little m a. So the first thing we need to do is we need to recognize what variables we need to get rid of. M and G and theta are fine, but the force of friction is not, because we want to have our answer in terms of mg, theta, and u, which is the coefficient of kinetic friction. So we need to rewrite this equation, which is the force of friction is equal to u, little k, of normal force. So now we need to find the normal force. So for normal force, we recognize there's no movement up and down. There's no wiggling. It's not bouncing on the incline. So the normal force is equal to the force of gravity. Sorry, it's mg cosine theta. My mistake. So normal force is mg cosine theta. So let me write that over here. So mg cosine theta is equal to the normal force. So we can plug that in up here. And then plug all that back down here. So I'm going to rewrite this equation as mg sine theta minus the force of friction, which is really the u, k, times mg cosine theta equals little m, the acceleration. Now all we have to do is solve for the acceleration. So we're looking for what the acceleration of the system is, or the acceleration of block A. So we divide off the m, and all the m's cancel. And the g's, we can pull one g out, so we get g times sine of theta minus uk cosine theta equals the acceleration. And that's our final answer. Okay. So the next part of our problem is to find the acceleration of block B and C. Now we see they're moving kind of analogous to one another. This one's moving up and this one's moving down. And they're going to have equal magnitudes of acceleration. So for our coordinate axis, we're going to set the positive downward and the positive upward. To the right. So this will give us positive accelerations, which makes our answer easier and less room for mistakes. So the first thing we're going to do is write the force diagrams for B and C. And then we're going to go to Newton's second law, and then we'll end up with our acceleration. So the first thing I'm going to do is over here draw B, and then draw C. So for B, we know that mg cosine theta is always in the downward direction, and mg sine theta is always to the left, or always down the incline. It's always slipping down the incline. That's always the trick to remember it. And to the right we have tension over the pulley from the rope. And upwards we have the normal force. So I'm leaving out one force because I'm going to include it in a second. Force of friction always acts in the opposite direction of motion, which is something to always remember. Except for in cases of static friction, but for kinetic friction, so when things are sliding, it'll always be the opposite direction of motion. So here, it's moving to the right because the pulley is pushing it down, the C is falling and B is going upward. So that means friction will be acting to the left. So we have plus the force of friction. So we have two forces acting to the left and one acting to the right. Now on C we only have two forces. We have the force of capital mg downward and the tension upward. So before I go into Newton's second law for B, which is what I'm going to use to find the acceleration, I want to find the force of friction and the tension. So I can plug those in because I see that they're going to come up in our equation. So the force of friction is probably the easiest one to start with, which is equal to u of k times the normal force. We're given u of k, but we're not given the normal force. But luckily we know there's no acceleration in the y direction. This block is not bouncing this way, it's just traveling along the slope. So there's no net acceleration and no net force in the y direction. So the normal force must be equal in magnitude to mg cosine theta. So we can write this as u mg cosine of theta. And that's one substitution we can make. And then the next one we want to make is tension. We know that because it's positive downward, it's going to be capital Mg minus tension equals capital M times the acceleration. So we're going to substitute in, we're going to write capital Mg minus capital Ma is equal to tension. So this is our second substitution we can make. So now I'm ready to write Newton's second law, which is the sum of forces equals little ma. And here it's going to be tension minus this quantity, which is two things. So it's going to be minus mg sine theta and minus force of friction equals little ma. Now we can plug in. So we're going to have mg minus capital Ma minus little mg sine theta minus umg cosine theta all is equal to little m times the acceleration. So now all that's left to do is solve for the acceleration. And so luckily it's pretty easy we're going to have capital Mg minus little mg sine of theta minus umg cosine theta equal to the sum of the masses times the acceleration, which will be capital M plus little m times a. Right? It's a distributive property. We can pull out the common a between these. Now we divide and we have our acceleration. So we have our acceleration of block B and C as equal to g times capital M minus little mg, little m sine of theta minus u little m cosine of theta, all divided by capital M plus little m. And that is the acceleration of our blocks.